Okay, so in this example we have two spheres, sphere A and sphere B. We're told that sphere A has a given mass and given radius, and likewise sphere B has a given mass and a given radius, and we're told that they impact one another, and that the coefficient of restitution for the impact is known to be given value of E. Based on the information, namely the initial speeds of the particles, we're asked to determine the velocity of the spheres immediately after impact. Okay, so to help us out here, I'm going to need to first of all draw a free body diagram of the system, and if we note that we're in the horizontal plane, maybe I should add a T there, what we'll see is that there's no external forces acting on the system. So perhaps more importantly to define is simply our n and t directions, and so I can go ahead in this case and define n to be through the center of mass of both particles, and t of course to be perpendicular to that. Now to help us out there, of course, we're going to want to have this interior angle. I'm going to call this angle theta, and so I'm going to try to reconstruct that. And to help us in that regard, I'm going to draw a little bit bigger picture here for you. And I'll ask you to note, we can do a little work here. We'll note that essentially B lines up with the bottom of A, and so let me see if I can do a little bit better job of this. And so in that regard, if we know that the center mass of B aligns with the bottom of A. Let me see if I can draw a good picture here. And we know in this case, this is a triangle that we get. And so in this case, let me sketch that triangle in here a little bit better. If the center of B is lined up with the bottom of A, we know this height here is simply the radius of A. And we know the hypotenuse is the radius of A plus the radius of B, and so we can take that information and find this interior angle here, which I'll call theta. Now we'll actually need that in the process of this problem, so let's keep that in mind. Okay, so now that we have that angle theta, namely we can say that theta is going to be, we have the opposite over the hypotenuse, so that's going to be the sine, so we say this is the sine inverse of the opposite side RA divided by the hypotenuse RA plus RB. We can actually go to work and try to apply the impact rules to the system. So in that regard, what am I going to say? Well, I'm going to say in this problem, we know first of all that if we draw free body diagrams for the particles separately, that the only forces acting on them will be the impulsive forces due to impact, and those will be acting equal and opposite in the n direction. And so as a result, we can say that linear momentum in the t direction, maybe I should just say linear momentum in t direction is conserved. And so since the balls aren't changing mass prior and post impact, what I can say here is that VA1 in the t has to equal VA2 in the t, where 1 and 2 designate pre and post impacts respectively. So now I need to find the component of the velocity in the t, and so to help us out with that, I'm going to draw a little bit cleaner picture here. Here's the n direction. Here again is the t direction. We know this angle is theta, which of course means this angle is theta. And if I have that angle is theta, then I know this angle here has to be theta as well. And so likewise this angle right here has to be the angle theta, and I can project this however I like now. And so if I do that, what's the initial speed in the t? Well, basically what I have here is a vector. Let me sketch this in here. VA1 looks something like this. And so if I want the t component of that, what I'm going to say is that I have VA1 times the sine of the angle theta has to equal VA2 in the t direction. If I do something similar on B, I can sketch it in a different angle. Here is going to be essentially VB1. And so if I use the fact that linear momentum in the t direction is conserved for that particle as well, I can say that VB1 in the t is going to equal VB2 in the t. And if I do my projection now, what I can say is, well, what's the initial speed in the t? Well, the initial speed in the t is going to be minus VB1 times the sine of the angle theta, and that's going to equal VB2 in the t direction. Now that I have those, keep in mind I want to find the total velocities of the system post-impact. I can move on to the other relationships I have. One of those relationships tells me that linear momentum for the system is conserved in the n. So if I want to write down now the total linear momentum of the system, I'm going to have the mass of particle A times VA1 in the n plus the mass of particle B times VB1 in the n is going to equal the mass of particle A times VA2 in the n plus the mass of particle B times VB2 in the n. Go ahead and do some substitution here. So this is going to give me MA. VA1 in the n direction is going to be VA1 times the cosine of the angle theta. And I'm going to have plus MB times VB1, which is going to be minus VB1 times the cosine of the angle theta. And that's going to equal, in this case, MA times VA2n plus MB times VB2n. Now, if you look so far, I have 1, 2, 3 equations, but I still have 4 unknowns, and so I have to go to one more equation. And the equation I'm going to use here is the impact rule. And so if I use that impact rule, it tells me that E is going to equal, in this case, VB2 in the n minus VA2 in the n divided by VAN and VB1 in the n minus VB1 in the n. If I do some substitution here, VB2 in the n is simply going to stay the same. That's a quantity we can work to find. VA2 in the n is an unknown quantity I'll work to find. VA1 in the n, we've already said is VA1 times the cosine of the angle theta. And I'm going to subtract from that VB1 in the n, which is a minus VB1 times the cosine of the angle theta. This is going to give me a fourth equation. And if I take equations 1, 2, 3, and 4, I can take those and I can recover 4 quantities, which I can use to find the answers to the problem. And those 4 quantities appearing in the 2 answers, namely the velocities of A and B post-impact, are given by VA2 in the t, which is of course in the E sub t direction, plus VA2 in the n, which is in the E sub n, and then VB2 is going to be VB2 in the t and the E sub t, plus VB2 in the n in the E sub n. So once you plug in those 4 unknowns that you get from your 4 equations, you'll have the final answers to this problem. It's a long process, but it's a process that's very straightforward as long as you remember in these impact problems, 4 equations, 4 unknowns. Alright everybody, best of luck.